Hi there, my name is Sherry from the University of Toronto, and here we present the paper Self-supervised feature learning for long-term visual localization. The goal is to use vision to estimate the pose of a robot relative to a visual map. However, appearance change caused by lighting or season makes long-term visual localization extremely challenging. One of the existing methods to cope with appearance change is called multi-experience localization, where it collects and stores multiple consecutive experiences with incremental environmental change to bridge a larger appearance gap. However, we want to localize directly against the top path without relying on any intermediate experiences. Alternatively, many methods use deep learning to learn local feature detector and descriptor that are consistent under appearance change. But these methods typically require large training sets with ground truth image correspondences that are hard to obtain. Hence, we want to learn features in an unsupervised manner. In this paper, we want to resolve the shortcoming by adopting a two-stage approach. We first use a sequence-based place recognition algorithm to obtain coarse image correspondences that generate training data, and then use a self-supervised feature learning network to learn feature detector and descriptors without ground truth pose labels. Let's focus on the first stage, which is to generate coarse image alignment. The datasets are collected as multiple sequences of image data, which is ordered by their collection type. We will call each sequence an experience. Each experience follows the same trajectory that starts and ends at the same location, and nearby experiences are more similar because they're collected closer to each other. To train invariant features, we need two input images of the same location. However, it is not trivial to generate such image pairs without ground truth pose information. Here, we propose to use a place recognition algorithm called 6LAM, which is a sequence-based algorithm that does not require any learning or sparse feature extraction, and is somewhat invariant to a certain level of appearance change. We first perform direct image correspondences by using 6LAM to match frames across two experiences. It will generate a candidate match for each frame. Note that at this step, we're only generating whole image matches, which is not good enough for metric localization yet. However, 6LAM has its own limitation, as it would struggle to match experiences with drastic appearance change. For example, 6LAM can't directly match experience 1 with 6, since they're too different from each other. To address this challenge, we compute the experience association graph under the assumption that neighboring experiences have closer collection time and are similar. We first order all experiences by their collection time. Then we perform direct image correspondences for each experience with its k neighbors. For each match, we compute a custom to reflect the quality of that match. In this diagram, a null represents the experience and an edge represents a direct matching. Then for any two experiences on the graph, we can compute the indirect image correspondences by finding the minimum cost path. In this example, we can indirectly match experience 1 to experience 6, using 3 and 4 as the intermediate nodes. All of these efforts are to generate training data in an unsupervised manner. After generating image correspondences, we can then sample image pairs for training. The next stage is to use the input image pairs to learn appearance invariant features, which can be used for metric localization. We will then focus on the second stage of the pipeline, feature learning. The network architecture is a UNet structure, where it takes an image as input and outputs the detected key point location, and along with descriptor values and associated scores. The feature training follows an expectation and maximization loop. During the E step, we compute the key point for the source and target image, and perform sparse key point matching to compute the relative pose change. We use ransack to reject outliers, which preserve the geometrically consistent key points. And during the M step, we use the estimated pose change from the E step as a supervisory signal to optimize the key points. For training, we train on two datasets collected at University of Toronto. The multi-season datasets capture the seasonal changes, and the in-adult dataset capture the lighting change. We perform experiments on multiple paths around U of T campus. And we plot the feature inlier for each repeat of the experiment for one of the paths. The red line indicates the minimum number of inliers for successful localization. We show that our method greatly outperforms the SURF feature. In addition, the unsupervised method achieves competitive results with the supervised version of the learned feature. Here's the video of the robot driving under different lighting conditions with matched key points. The path is taught at noon and is repeated in the outdoor environment throughout the day and achieved a 100% autonomy rate. We visualize the matched key points in layers overlaid on the teach images, and the live repeat images are shown below. As can be seen from the video, the learned features are robust under different lighting conditions and can be used for localization even during the nighttime, where the robot are driven with only the headlamp. In conclusion, we propose the novel self-supervised feature learning pipeline, where we generate training samples using place recognition and train features without any ground truth pose. Secondly, we validated the learned feature by integrating with the visual teach and repeat framework and demonstrated a successful closed-loop localization experiment for a total of 22.4 kilometers. Thank you.